Mohan from AML department second year. So today I'm going to talk about on the topic of matrix addition with unified memory in CUDA unified memory. So this presentation will be on what is unified memory and what are all the roles and efficiency of unified memory and how it increase the performance in GPU architecture. Through matrix addition, we are going to see it. So matrix addition involves adding the response elements from two matrices, resulting in a new matrix of same dimension. So the operation is foundational in linear algebra and critical for various applications, including scientific computing and data analysis. So why we are taking matrix addition is that it's a basic concept or a basic instruction we are going to do in GPU, because in GPU we are not just gonna use like complex mathematical problems, very simple mathematical problems to render the graphics cards or like rendering the videos, images, etc. Maybe for RGB lights, we're gonna use some a bit calculative or complex mathematics. So the problems or the applications in the computational problem, we can able to see that it's widely used in image processing, as I said, for pixel values from two images are combined, and in scientific simulations that model physical systems. It plays a key role in the algorithm that requires intensive numerical calculation, facilitating faster and more efficient data processing. So we are going to compare that CPU is GPU performance, and how the host or the CPU we can able to say as host and GPU as the device. So how the performance differences has is being seen in matrix addition. So when comparing GPU and CPU performance for matrix addition, GPU demonstrates superior speed due to parallel processing capabilities. CPU performed operational sequentially, which led to slower execution time for larger matrices. So as we said in the example that if you are taking a long queue, in that long queue, if all the instructions are in a single stretch, but in GPU perspective, or there will be having multiple queues with limited number of instructions, such that the speed can be increased in that time. In the contrast of GPU leveraging thousands of core handle multiple data points simultaneously, significantly reducing the time required for complex calculations. So that's why I said. So now we are going to see about what is unified memory and how it has been used in the GPU process. So the concept of unified memory. Unified memory is a memory management feature in CUDA that enables both CPU and GPU access the same memory space without needing explicit data transfer. We can able to say that it's a common place for GPU and CPU to access for more memory. This approach simplifies the programming model, allowing developers to write code without worry about manual transferring data between host and device, thereby enhancing the productivity. So if a code has been written in the device, the host need to first transfer the data, and the data will be sent to the device. After that, device need to process it or evaluate it, or we need to run it. After executing it, we need to again send it to host, and we need to display it. So this will be a hassle-free thing that by using unified memory, the both the GPU and CPU or host and device can be using the same uh, memory for data transfers without any additional time, which can reduce the latency and increases the performance in the context of it. So the benefits of the memory management. The use of unified memory simply simplifies memory management by automatically handling data migration between CPU and GPU, because it's a common place where we can access both the data. This eliminates the cumbersome steps for memory allocation, copying, and deallocation, which reduces the potential of error and streamlining process development. As a result, the developers can focus more on optimizing algorithm rather than managing the memory. So the impact on code efficiency. So how it has been impacting, like the factors like throughput or performance, as I said, delay or latency. Unified memory contributes significantly to code efficiently by minimizing boilerplate code associated with traditional CUDA programming. With automatic data management, the overall code becomes shorter and more readable. This is not only enhances maintainability but also allow their developers to implement algorithms quickly, facilitating faster iteration and more effective optimization. So, as we said that we mainly use GPU for parallelism. So, to enhance the parallelism, we use unified memory in this to not bother about the data management. So, now we are able to see the code. So first we are going to import all the packages for the program to be executed. So this is a collab and we are going to run it on the runtime of T4 or Tesla 4 in GPU for Python, and also we are going to import some uh, other files like NVCC, like pip install git NVCC for Jupyter Git. So this helps us to run the CUDA code. The CUDA code will be generally in the C++ format. So for that to run in the Python environment, we need to install this packages before. So now we need to import the as first before the packages. We need to give the magic name of CUDA, and we are gonna initialize macro for checking the CUDA calls. So this and all the basic definitions for executing the programs. So this is the function which used to get the current time or elapsed time we can able to get by this, and initializing the data on the host side. So initializing the data matrix. So as I said that we need to transfer the data from host to device. In this first we are going to initialize the matrix from device side, host side. So after that we'll be performing the matrix selection on the host side and we'll get some result in it. So this is a comparison the host and device, that how much time difference has been taken between them, and this is the upper part is for host or CPU part. Now it's for GPU part, such that we need to initialize a kernel launch for it, and after that we are going to initialize the thread index of the elements. After that we are going to perform the addition or matrix addition. So for that we are going to use CUDA malloc managed for the unified memory access for the host and device. So this is for A matrix and B matrix, and this is for the result for GPU and host. After that, here we are going to initialize elapsed time, or we are going to get the elapsed time, and performing the matrix addition on the host side for validating it, and we are going to get the CUDA block and grid. So this is because why we are getting that, to get kernel launch, like we will be using this function bracket grid comma block to be initializing in the device. So after that, after all the validations and checking the results, we'll be freeing the unified memory. So now we can able to see that first the memory, the matrix size is 4096 and 4000 x-axis, and in the 2D array of 4096 and 4096. So the initialization time is 0.6 seconds approximately, and the time taken for the host to calculate is 0.05 seconds of thread of it, as we can see here of the thread block and thread. 128, 128 and 32, 32. But the time we take on GPU is that it's very minimal. So it's 0.0004. It's something like 2 into 10 to the power 4 minus 4 seconds. So which is comparatively having less delay and more efficiency in a large data set, we can say. So hereby I conclude that incorporating unified memory into CUDA applications yield a notable advantages, including simplified memory management and dramatic improved execution speed for matrix operations on the GPU. By leveraging the unified memory, developers achieve cleaner code, reducing the complexity of managing data transfers and allowing for more efficient workflow. Thank you.